Hi, welcome back. In this section, we are going to look at the implementation of the robust autoencoder technique on a real-world data set. And let's get started. Thank you. So, as suggested, we'll be talking about the robust autoencoder being applied to real-world data. Just to give you a background about the data set, we are considering the Sydney Harbour Bridge data, which has been instrumented with accelerometers. So there are about 800 joints which are monitored across the span of the bridge. So in this case, we are considering only 2 joints, and hence the name 2 joint in the experiment name. So there are about 3 sensors being placed, 1, 2, 3 sensors, and the data is being collected at the rate of 375 hertz for about 1.6 seconds. And there is a known damage in one of the location, and the data collected from the sensors related to this location will be deemed as anomalous and will be used as anomalies for evaluating our set of models in the in the experiments conducted. So just to give you a brief background, so the set of features what we consider here has 2 types. One is the raw data, or we can apply certain fast Fourier transformed transformations on the raw data set to obtain the FFT features. And there's a set of standardization being applied by applying z-score by making sure that the data is zero mean and divided by 1 standard deviation. And as stated before, we evaluate the model, the robust autoencoder model, on both raw and FFT features, and one of the experiment will be discussed in this section now. So let's hop on to the Google Collab notebook. If you have not seen the Google Collab setup instructions, I kindly request you to go visit the video where you can have some setup instruction as to how to set up this Google Collab environment for you to execute the experiments. So once you have set up the experiment, in this section of the code, you are mounting the directory, the Google Drive containing the experiments. So once the mount is successfully completed and all the required libraries are loaded, you will be able to see the section for the robust autoencoder based experiment based on the FFT features. So here the data dimension considered is about 900, and the pre-processed FFT features file has been loaded on in this experiment, and we consider the robust cost function for the autoencoder, so hence the name RCAE here. And if you are using images, the same set of the architecture of the robust autoencoder needs to be included appropriately, suiting either by using a normal autoencoder or a convolution based autoencoder. So here we have the configuration settings for the experiment, and you can review the configuration file for certain hyperparameter settings and what sort of hyperparameters are being used for this set of experiments. And the file here, RCAE, contains the implementation of the robust autoencoder as well as the robust convolution autoencoder implementations, which was discussed in the slides. The robust convolution version will be used when working with images, whereas the robust autoencoder version has been used when dealing with a time series data such as structural health monitoring data collected from the bridges. So here, let us we are having one method like the fit and the predict, which trains the model, the robust autoencoder model, and predicts considering the test data, using the test data. And the dimensions of the train and the test data has been locked for logging purposes here, and the evaluation metric considered here is the AUC, and it has been produced across different set of random experiments, and you can set the random seed to be a list of 10 digits where every time random seed changes, the set of the train data which is chosen changes. So by evaluating this across for many random seeds, we can ensure the execution of the model is quite robust enough. and across various runs. So let's visit the RCAD class. So the RCAD accepts a few parameters for initialization within the class. So let's visit the RCAD class. So once it accepts the parameters, it conducts the initialization process, and if the data set is SHB, which is structural health monitoring for the Sydney Harbour Bridge. SHB is the short form for the Sydney Harbour Bridge, and we have a separate data loader being defined in this file, the SHB file, which takes care of loading the respective data. So the SHB file contains a function called load data, which is responsible for loading the data and bifurcating it into training and test data, and it's also responsible for applying any transformations such as the z-score, and if we are loading the raw data, we'll be using that to convert into FFT by applying certain frequency transformations as such. And you can choose to apply a scaling by setting the suitable parameters in here. And yeah, so so once you have loaded the data onto the as a train and test set of NumPy arrays, so the fit and the predict method pulls the data which has been loaded, the train and the test data, and if it is we are discussing with respect to the Sydney Harbour Bridge experiment, and if you are considering the CFR10 image data, if you want to load the CFR10 image data or any other data of your choice, you could add a section here to load and continue with the algorithm. And once we have loaded the train and the test data, we could define both inductive as well as non-inductive mechanisms depending on how we want to choose to run the experiment. So this is an optional scaling being applied. Certainly this has shown to when you scale the images by 255, it is shown to perform or obtain better converging results. So hence this scaling has been applied to the training and the test data. So let's focus on the set of the RCAE implementation here. So the lambda set can be chosen from a set of list here, and the evaluation of the robust autoencoder can be done for various values of lambda. So as a experiment, for the sake of the experiment here, we have considered the lambda to be 0.6, and once we the main objective is to learn the value of n, the noise matrix, using the soft thresholding technique as discussed in the theoretical section of the slide. So kindly visit the intro section of this experiment to understand more about why do we apply the soft thresholding technique in order to learn the noise which is present in the data, which is a representative of the outliers. So here we call the function which computes the soft thresholding or for the chosen architecture model. And this section here, once the autoencoder is trained with the robust cost function, it performs the relevant predictions and obtains the metrics of interest. So let us go inside on the compute threshold function, which is written in the shb.py file. So in here, it takes in the value of the n and lambda for a chosen value of lambda. So we could choose between different architectures, whether you want to normally choose an autoencoder or a convolution based autoencoder. And let us visit the fit baseline A, which is a normal version of autoencoder instead of convolution. So if the method chosen is the RCAE or RAE, in this case, in case of convolutions, and in case of autoencoder, we choose the method to be as AE. If it is a normal AE, we choose it as with the normal loss of mean square error. If we are choosing the loss function as robust cost function for the autoencoder, we'll be using the custom loss RCA loss defined. So let's take a look at the loss function here. So if depending on the type of architectures, we would be accessing the weights of the network, U being the weights from the input to the hidden, the first layer after the input. Input to the neural network architectures from the input to the hidden, U representing from the input to the hidden, and V representing from the hidden to the output layer. So you may choose the weights for U and V accordingly, and the value of noise which is being initialized and computed through the soft thresholding technique. And the custom RCA function has been implemented in accordance with the formulations described in the intro section of this tutorial. And we have term 1, term 2, and term 3 respectively, wherein the term 2 and term 3 respectively mainly refers to the regularization parameter, whereas this accounts for the reconstruction error what we obtain based on the true and the predicted value of the results. So this is the robust cost function that has been implemented and attached to the autoencoder architecture, and the same could be extended to convolutions if you're working with image-based datasets. So this set of fit and predict works for different set of random seeds by choosing train and different set of train and test data, and the same could be executed if you have properly set up your Google Collab environment. So I hope this video explains the implementation of robust autoencoder and helps you to customize the code for your dataset and the experiments of your interest. Thank you. See you soon.